Good morning. How are we doing, Ignite students? It's a great day. Let's talk. We're moving on. So we've got, if you're keeping up, we have Thursday, Monday, Wednesday, and then spring break. So we've got 3 lessons to kick in here, and then we've got break. You could take some time off, and then we're going to pick right back up where we left off. We're going to go forward. We're looking at weathering, erosion, changes to rock on Earth. Okay, different things that are happening. So we're going to start today. We're soil. That was the other. Soil weathering changes to rock on Earth. We're going to start with weathering. Real simple. This is a lovely picture of Half Dome. We'll get to that in a minute. But weathering, the basics, there's chemical weathering, there's mechanical weathering, and all of it just breaks down rocks. It breaks down rock and it increases the surface area of the rock. So one little thing, since I happen to like teaching math some days, we're going to talk about the surface area. How does breaking this rock up, even though it doesn't increase the weight, doesn't increase the volume, how does it increase the surface area? Because if you just split this rock in half, or in half, and then in half that way, now you have 8 cubes. All right, first of all, length by width. This is 3 by 3. So you've got 9 square inches on this side. 9, 9, 9, 9, 9. So 6 nines gives you 54 square inches. Split it in half. 1.5 inches by 1.5 inches. So that's 2.25. That's 2.25 square inches for this face. But this has 6 faces like that. This one, this one, this one, this one, this one. All of them have 6 faces. So 108 square inches. Basically what happened is you opened up. This light shade over here was not exposed before, nor was the one it faces, nor was this bottom one or the one above it, or any of the ones in between. And so every time you split a rock, there's more surface to be exposed. If you're an ice connoisseur, big chunks versus little bitty crushed pebble ice in your soft drink, right? The crushed ice has more surface area and will cool your drink faster and make the drink taste different if you're an ice connoisseur. All right? So there's that. Hey, look, it's the same thing, but now they made it a rock inside. So if this is 2 by 2, well, that's 4 on top, 4 on the front, 4 on each of the 6 sides. You got 24. But now you cut it in half and you got 1 by 1. But then you've got 6 1 by 1s times those 8 cubes. You've got 48. And then if you did it again, half by half, all the way around, 6 times 6, but now you got 64 cubes, 96 square units. Surface area goes up quickly. That's all. Hey, look. All right. There are 3 processes we're going to talk about first when we talk about physical weathering. These are the White Cliffs of Dover. All right, they're very chalky. They are incredibly white, and this was a fairly recent 2012-ish. Maybe it's 2001. There were a couple recent slides on the web that this was talking about. They stay white because of erosion and weathering and erosion. Remember, weathering is the breaking it down. Erosion is the moving it away. So as all of this was weathered and fell, it will be eroded as the tides come in and tides bring it out and slowly pulled out to sea or down to the bottom. Weathering breaks it down, erosion moves it away. But what actually got in here and caused this at the top to fall, so you got a little crack right here, water gets down in that crack. Water freezes, water expands. That puts pressure on all sides. And then water freezing is huge. This is done by frozen water. This is frost wedging. All right. Water that freezes expands like 9 times. And if it's in a little bitty crack in rock, it's got nowhere to go. The pressure builds in these huge pressures, and you could create these lines and these fractures all across the rock. I think we've got one more. Here we go. I meant to have another image here. So when these start to fracture and stuff, you can get all of these. If these fall down to the bottom of the mountain, you can get a talus down at the bottom, which is just this big pile of these huge chunks that have been fractured off. I was going to be funny and put up something from the stone talus from Breath of the Wild or something. I don't know. Meant to have another image. Sorry. All right. So that's frost wedging. Fine. Easy. It's the same thing that burst water pipes. When water freezes, it expands. It's a weird substance that way. Most substances expand as the temperature goes up. Water, right as it freezes from 4 degrees Celsius down to 0, goes the other way and expands as it gets colder. So there's a dip, and then the water expands on both sides. Well, it expands right as it turns to steam, and expands as it freezes. So frost wedging happens a lot more in mountainous areas. Why? Because you wake up and it's the high 20s, and then you have a nice 45, 50 degree day. Like we had that 2-3 weeks ago in the spring. You would wake up and it'd be freezing, but the sunny day, and it would be 40, 50 degrees. But in mountainous areas up high at high elevation, if you have that daily, this 3 freeze thaw cycle, pressure, relax, pressure, relax, pressure, relax. If you do that over and over and over on here, you're going to build these cracks up and you're going to fracture the rock. Okay. The next one is one we don't hear a lot about. The next one is unloading. And unloading may just seem like a big relaxation. So unloading, actually, you get these huge uplifts. Do we remember when you get this igneous rock flow in from the bottom and just lift up huge pieces of granite, or raise it up and you just have these huge bumps? Well, that's great. But when you get that rock that used to be under the earth, when you lift it up and above the earth, now there's no weight on top of it. There's no pressure on top of it. And when it goes and relaxes and expands, you get peeling. This peeling is called exfoliation, right? That's the little outer layer of skin right there. You're lifting that up and off. It's because of this unloading. You have taken the weight off, and now this outer layer, the rock with no pressure on it, starts to turn back into layers, and this outer layer just pops off almost. All right, there's no pressure on top of it, so it unloads. Okay. This is common in granite. Let's see if we've got another one. Here are some examples, some really important examples of unloading. This is Half Dome. This is one of the most impressive things Yosemite's got. So there's a huge granite uplift, and then the weathering that's happening on it is layering. The outer layer is flaking off. It's unloading. It's exfoliating. All right, let's see what we can do here. You can see some of those layers, some of it starting to turn back into layers, what used to be really compressed back into each other. So let's see if we've got another example. In geology, there we go. I mean, just you can see there's nothing else causing this to become layered. It's without the pressure on top of it, it does so. So, all right. So you are on the Mist Trail, okay? So Nevada Falls, Liberty Cap, the back of Half Dome, all of this is in Yosemite National Park. One of these days I'm going to travel out there. Everybody's got a bucket list, right? Okay. We're going to take... When did I lose my... Oh, there we go. So we're back. That was, sorry, just a quick pause there and cutting the film. The uplifting, the mechanical weathering in the Half Dome that you see, all of that is great. Let's look at some other things. So we've got frost wedging. We've got uplifting. What about biological activity? Plants and animals. Plants and animals do cause weathering. Here we go. Trees, trees are crazy because this tree, sometimes it looks like the tree is hanging on and like the tree started to fall off, and then the other times it looks like the tree pushed the rock off. We don't know, chicken or egg, who came first. But as the water here, as the stream erodes from under the tree may start leaning over, pushing more on the rock. Or if there's just a little bitty crack and the tree seed is planted in the crack, as it grows, it will force the rock off. Depends on that specific situation, right? Both can happen, but you are weathering and breaking these rocks down through tree roots. This one, you're not weathering. There's no water running past it. It's not running through there. This, I know this is a stock photo, but this is also, I know it's concrete and sidewalk, but this is something you'll see a lot where tree roots will bend and break pavement, sidewalks especially. All right. Animals, there were just too many to look for. Animals cause weathering and erosion, whether it's, so I just was going to show you, look at all the animals digging. It can be burrows, it can be nests, it could be whatever. There's just a lot of ways that animals dig into these places. So all of those plants and animals together are biological weathering. So there you go. You've got frost wedging, you've got unloading, and you've got biological activity. I don't want to see that one yet. Now, switch. Chemical weathering. There's several different things chemical weathering can be, but basically you're forming the rock into one or more new compounds. So where mechanical weathering is just breaking into smaller pieces, but it's made of the same stuff, chemical weathering is transforming it into a new compound. Okay. Water everywhere, and not a drop to drink. Water is the biggest chemical weathering agent on the planet, period. That's it. Now, water's not, well, we don't think of chemical, we don't think of dangerous chemicals, we don't think of water first, but water is the most abundant, readily available chemical, and it weathers a lot. It falls from the sky. It's raining right now as we speak. All right. Water is a very good absorber. So it absorbs gases, whether they're from the ground or the air, or in it, you then dissolves those. And if it's got, say it's got dissolved O2 in it, well, that makes oxides, and the oxides rust things, right? You can turn it into iron oxide. If the water falls through the air and it absorbs carbon dioxide, then it makes carbonic acid, which is the same thing in sodas. It's a weak acid, but that's acid rain, and it will fall on everything. There are other things that make other, if the water absorbs sulfur or nitrogen oxides from pollution, from burning things, it makes other types of acids, which make acid rain. All of these get you chemical weathering. All right. So granite is probably, I like this image. How did I go backward? There's the image I wanted. That was just the search for it. Here's the image. Big image. All right. On the left, this is sharp, clean, new, fresh granite. Sorry. Over here. Over here, what you have is chemically worn granite. What do I mean? Okay. So we get a little bit of CO2 dissolved in water. So you got carbonic acid, and the carbonic acid falls on granite. You're like, granite's a rock. Nothing's going to happen. Granite's my countertop. Ain't changing, right? It takes the feldspars that are in here. Oh, because we remember that granite's made of feldspar and quartz. I know you remember that. So it takes the feldspar in there and it turns it into clay. And then the clay starts to wash away. And the quartz isn't really chemically affected by the carbonic acid, by the rain. But if you start taking the clay, the feldspar turns into clay, and if you start taking that out from around it, then the quartz starts to be released, and the whole thing starts to weather and roll away. The clay, being really small in size, gets washed a long way away. The quartz, being bigger chunks, doesn't wash as far and stops and ends up on the beach. That's where you get your quartz in your sand. and the clay in the silt in the ocean bottom. So fresh, weathered, dull, clay like out here. Okay. Other things. So oxidation. Okay. Oxidation. You can rust things. If there's iron in this rock and it rains on it, you can create rust. And it doesn't just have to be iron oxides. There are other oxides you can create that give the same browning and the same rust-like effect. Okay. Um, let's see. You can expose acids. So any kind of the rain changes the pH. Um, caves. We're not even talking about in caves. We're talking about exposed rock usually, but caves, there's all sorts of stalactites, stalagmites. There's all sorts of chemical weathering happening inside there. Okay. All right. Gravestone weathering. This one's kind of interesting. Let me see. I wrote this down. Marble goes faster than granite. Okay, this is interesting. Why gravestones? Well, one, some people like to preserve history. Two, they're everywhere. And three, you know the date it was installed should be written on there. So if I know this is 100-year-old and I can look at what material it's made of, I can see all the things that's happened and I can compare that this area that had the same weather, look at these two different rocks. One was a marble headstone, one was a granite headstone, one was limestone, one was sandstone. What do the inscriptions look like now? What do they look like after 50 years? What do they look like after 100 years? You just go to different parts of the same cemetery because the weather would be the same in that location. You go to another location and you do the same. Gravestones actually kind of work and help like that, right? Marble typically erodes, weathers faster than granite, even though we just talked about the granite one, right? So weathering factors, let's see. Yeah, we don't care about that. Let's see. Sandstone. All right. Flaking, sandstone flakes. That's a sandstone headstone. Limestone. Limestone is soft and porous, right? Cave-like. You're going to get some pitting. Marble. Okay. Few years old tend to be very smooth, good luster. They lose their luster. They're gritty after 10 or 20 years, right? Okay, cool. Granite. No good picture, right? It takes a while, but you are going to weather it. Classification of the weathering. This is all sorts of stuff. But either way, it's gravestones are an interesting technique for looking at weathering in context and having lots of dates and lots of places to sample. And you can do it without being disrespectful to the deceased. Okay. Spheroidal weathering. One last little thing I wanted to get you. This is, there we go. We'll just do here. The spheroidal weathering, basically, it is chemical weathering, but the chemical reaction is going to be more intense at a corner or an edge, an exposed corner or an edge. So everything rounds off is what spheroidal weathering works out to. So yes, those frost wedges that we saw had big sharp lines through them. Even whether it's frost wedging or chemical weathering, if you wait a while, you're going to round all your corners. Okay? But especially with the chemical weathering, you're going to round all your corners. And so as water goes through here, you're going to, yeah, maybe that was a frost wedge, but you're going to round. Usually frost wedge is a more dramatic thing. Happens faster and it pushes more. You're going to round your corners, and that's what spheroidal weathering is. All right. That's quite a bit of weathering information. Okay? It's happening to rocks all the time. They're constant movement. The face of the earth is always changing. Everything's weathering if it's outside. Even the rocks, the pyramids are slowly weathering and will not be there forever. Okay, now that I've ended on that macabre note, everybody have a good day. We'll see you soon.